Hello, welcome to another chemistry video. Today's topic, molecular geometry. This will have a very brief overview of molecular geometry, and I've also thrown in intermolecular forces. So after completing this video, students will be able to predict the shapes of molecules or polyatomic ions using VSEPR theory. Okay, what exactly is VSEPR theory? VSEPR stands for valence shell electron pair repulsion, and it is really one of two theories that are used to explain molecular geometry. I don't really discuss the other one here, so if you want to learn about hybridization, you're going to have to find another video. Electrons have the same charge, so they don't want to be by each other. The same charges repel, opposite charges attract, yada yada yada. You've heard it before. They'll push as far away from each other as they can. The bonding of atoms prevents electrons from moving too far away. It's similar to points on the circumference of a circle or points on a sphere. These electrons can only go so far away from each other. The unbonded electrons, which is a term you're going to hear, they're lone pairs. If you remember back to Lewis structure, we had the dots around a Lewis structure. Those are the electrons that are not used in bonding. Those are unbonded electrons. Lone pairs that still occupy space around an atom, but only the atoms determine the shape of the molecule. Okay, here we have some patterns. If we're talking about a molecular geometry or a shape that is called linear, there are two possibilities here. There's the possibility that there's only two atoms or ionic bonds. If you've got an H2 or an HCl, either one of those has just two atoms and it'll look linear. It doesn't have a choice. We've made the jump here to three-dimensional, and you're going to see that before long. Lewis structures were flat two-dimensional creations, and molecular geometry actually shows us that there are three dimensions. Okay, in red here we have, and you'll see these as we go through this table, we have patterns. The A could represent an element that is in the center of our structure, and the B represents the atoms that are bonded to the central atom. So for example, if we had beryllium and two fluorines bonded to it, beryllium would be the A, and the fluorines, there are two of them, would be B2. And that would look something like this. Okay, our next shape, trigonal planar. We've got A, central atom, and B3. In other words, there's three atoms bonded around it. So we could have aluminum and three chlorines. It'll end up looking something like this. Another example would be boron and three fluorines. Okay, another possibility, bent or angular. I have one central atom, two atoms bonded to it, and this E here is something new. That stands for unbonded pairs of electrons. So in water, when we show our formula, you can see that there is one central atom, oxygen, and two hydrogens bonded to it. But this you can't see, the E's, the unbonded electrons, unless you draw a Lewis structure, or you just happen to know them. But it ends up looking like this. And the reason this is bent, and not like the linear one up here, this is bent because there are unbonded pairs of electrons on the outside of this central atom that will push away from the electrons that are used for bonding. So they're still trying to get as far away from each other as possible, but they're still bonded to, they're still attached to the central atom. Okay, our next shape, tetrahedral. Our pattern is A, central atom, and B, 4. So 4 atoms bonded to the central atom. You could have CH4, methane gas. You could have silicon bromide, SiBr4, 4 bromides, and it ends up looking like this. Okay, and the last one we're going to talk about in this video, there are many molecular geometry shapes. I'm just going to cover a few here. Trigonal pyramidal. And our pattern here is A, central atom, B3, so 3 atoms bonded to it, and 1 pair of unbonded electrons. So you could have ammonia, NH3, or you could have PCl3, phosphorus chloride, 3 chlorines. And the reason it's not flat, like we have with the trigonal planar up here, is we have a pair of unbonded electrons again. And once again, if you think of this as a sphere, all the electrons trying to get as far away from one another as they possibly can. Okay, that's all the shapes I'm going to cover in this video. Let's talk about intermolecular forces. These are generally weaker than forces of a bond, but they'll still hold things together. Boiling point shows the amount of energy needed to break intermolecular forces of a liquid. And the boiling point for ionic and metallic bonds are much higher than for molecular compounds. It takes more energy to separate electrical attraction. Okay, a dipole is a situation where molecules of equal but opposite charges exist and are separated by a short distance. This is very common in water, in ammonia, carbon chloride, CO2. And as we go through, I'll explain to you why they're so common. I'll have pictures and everything. It'll be so cool. Okay, molecular polarity and dipole forces. These represent the strongest of intermolecular forces. Generally, this means an electrical attraction between atoms that are oppositely charged. You could have a hydrogen with a positive charge on it, and maybe an oxygen with a negative charge on it. And yes, they're bonded together to be neutral, but if you remember from electronegativity, one atom is seen as having a stronger pull on the electrons than the other. And so that sets up a situation where one end of a molecule might be more positively charged and the other end might be more negatively charged. And that's how we get these dipoles set up, or this molecular polarity and dipole-dipole forces. So let's talk about hydrogen bonding, which, to be honest, is actually a special application of the dipole forces. Okay, the intermolecular force in which a hydrogen atom that is bonded to a highly electronegative atom, such as fluorine, oxygen, nitrogen, chlorine, it creates a really polar bond, as I was just explaining on the last slide. But a highly electronegative atom is attracted to an unshared pair of electrons of an electronegative atom in a nearby molecule. Do you remember when we talked about the molecular geometries just a minute ago? And H2O, for example, was seen as bent or angular. Well, it was bent because there were, let's say this is a water molecule because that's what it's supposed to be. We have two hydrogens here, an oxygen, and we have unbonded electrons out here on the outside of this oxygen. They're trying to get as far away from these hydrogens, the electrons used in bonding, right? So that creates a very negative place right here and very positive ends of a molecule here. So if this is very positively charged, a hydrogen, it could be attached to the next molecule of water, the unbonded electrons. Hydrogen's very small, it can get in really close to unbonded electrons. It won't bond with them, but it will be attracted, because here we have positive, here we have negative. And if that goes throughout your whole sample of water, it kind of tends to hold it together. This is the reason why if ever you spill some water, it sort of beads up or puddles up. It doesn't just fly everywhere. It's water sort of sticks together. Okay, so let me read through the rest of these. Hydrogen bonds to an element with a high electronegativity, such as fluorine, oxygen, nitrogen, or chlorine, creating a very polar bond. Hydrogen has a small atomic radius, and so it can get closer to unbonded electrons on other atoms. And this creates a situation where there's an electrical attraction between the hydrogen and the unbonded electrons of nearby atoms. Our last slide, London dispersion forces. Electrons are constantly in motion. And at times this may cause a very weak attraction between atoms because intermolecular attraction can happen if we have all the electrons tend to migrate toward one side of an atom. Let's do this here. Let's draw an atom. That's not very good. Okay, so we've got some atoms, and the electrons are always moving around. Well, if at some given time, all the electrons end up more on this half of the atom, that'll create this side being very not negative and this side being very positive. Now, if the same thing happens here, all our electrons end up somewhere over on this side, or most of them. This becomes, whoops, I did that backwards, didn't I? Scratch that. Start over. My doodles got ahead of me. Okay, so if all my electrons end up on this side, anyway, that creates this being very negative, this side very positive, and we could have an electrical attraction. Now, as electrons are always randomly moving all over the place, this isn't going to last for very long. It's not going to be a very strong attraction, but the idea is that this intermolecular attraction could actually even affect noble gases. More electrons generally means a stronger force between the atoms. So I hope this video helped you out a little bit with molecular geometry and intermolecular forces, and we'll see you next time. Thanks for watching.